Alright, this is Cis-125 Introduction to Programming. We're already on week 3, day 5. This is Tuesday. Tech review. Do a bunch of that first. Talk a little bit about top-down design and IPO. Sequence, we really don't add to that today. We did do some Python. Students should be working on their computing circles, and we do a little bit of work here at NIAC, how we're going to handle the code. Thursday we'll talk more about sequence and have a quiz. Alright. We talked about coding, and I asked the students to think about what do you think of as a programmer, software developer, full stack development. What does it mean to go to a boot camp and get your programming skills? You can learn online, all kinds of coding. And then we looked at code.org and we watched the introduction video at code.org. In there they talk about breaking down problems. Code.org started in 2013. It's this idea we need more coding, or you might think of it this way, computer science schools, K through 12. And I'm a big proponent of that. Not only to have people become aware of coding, but to teach computational thinking. FYI, full stack is where you do the web development, the database development underneath, the back software programming, user interface to make all that work. It's the full stack of things. And of course that's very popular with the use of the internet and the web now. So the students talked about some of these things. You can use tutorials to learn, you can go to a boot camp to learn, you can use code.org to learn coding, but to have a fundamental understanding, to be a software developer, you probably need a pretty good tech background. So we cover some of the basics here. So we talk about 4 things for every computing system, whether it's your phone, microwave, a car, a PC, a laptop. Somewhere there's some kind of physical hardware. There's software to tell the hardware what to do. There's people to use it and develop it. And then we have a way to connect them all together. Connectivity between. Alright, so let's take a look at this. So we talk about hardware, the physical equipment. And what typically communicates with the hardware is the operating system. That communicates with the hardware. We have applications, which we're writing in this class. That communicates with the operating system. Typically, there are cases you can write applications to deal with the hardware, but that is not common. And then we have our users and experts. They communicate typically with the app, especially the user. Now the expert, we would like the expert to be able to not only develop and communicate with apps, but know a little more about the operating system and know a little more about the hardware. The more you know about those, the better you'll be able to deal with technology. Alright, we talked about data. Data is transformed to information using software. So let's go through that. Data can be the raw facts. So we got the information stored either in data files, okay? 1s and 0s, bits, representing the data. Software can take those bits and make them information, make them value. They can play a movie, do a calculation, keep track of a Word document, maybe, I don't know, listen to music, all the things, communicate, lots of communications. So the software makes it happen. Don't confuse this. Some people say data is taken and stored as information. That's not typical. It's not the way it's done. Usually it's converted to information. The information is something us humans can digest and use. It has value. Another thing they say, bits are converted to information. Bits aren't, they are converted to some type of information, but they're still bits. They never change from bits. They don't change from bits to words. The software takes the bits and makes the words out of them, if that's a better way to do that, to think about it. Alright. Source code. This is something humans understand. We take the source code and we compile it into object code, something the machine understands. We compile, or we interpret it line by line, or we compile it. Compiling goes line by line, but it converts it over. Interpret it doesn't leave it in compiled form. It gets interpreted every time you execute the program. Then we can bring in from libraries other code that's important, and then we can develop an executable that will run on a computer. Okay? So this is something humans understand, converted into something the machine or the device understands, and then it could be linked, bring in other things into something that's executable. And where does that happen? You can have your software stored somewhere. You bring the software into memory. Okay, like Python. We bring the Python programs into memory, then they're interpreted. The interpreter checks the code and then starts executing the instructions. If it's a executable already compiled, then it's just brought into memory and the lines are executed. The interpreter doesn't have to do any work because it's already compiled. Key thing here, if a program's going to be executed or performed, it has to be in memory. And the memory, the processor then communicates with those instructions. Do the arithmetic, make logic decisions. Here, arithmetic logic unit. Now here I mentioned flash in your device. These two could be considered as one, actually, in your device. Typically. File names in Linux, caps and smalls make a difference, and for programming class, don't use any spaces. Alright, so we can have, let's go through this, we can have a problem, and then we can solve that problem by analysis. Do we understand the problem? Let me use another color here. You can't start designing until you understand the problem. That's where we talk about. You have to understand, what are you going to put in, what kind of processing are you probably going to need, and what do you want out. IPO, input, process, output. You need to understand it before you can design a solution. When we design a solution, we use, in here we're going to use control structures. It's either going to be linear, conditional, or some kind of loop. So you design it using either flowcharts, pseudocode, or some combination of those two. So that would be in the design process. You do a walkthrough, test it, and so forth. And then you develop it, you write the code. You can actually pick the language at this point, write the code, test the code, make sure it works. When you implement it, that's where you put the code into use. Okay? And then you evaluate to see if it's really doing what you want it to do. This isn't necessarily testing it. You should have tested it before you put it into use, but you evaluate. And then in the big picture, you keep checking And then if you find something that needs to be fixed, you can go back up, analyze the problem, and go through these steps again. Now, what do we use to design programs? We either use, let me go here, sequence. We use a combination sequence, one thing after another. These are process boxes. As an example, pseudocode, you'd have an action word, and then what it does. Excuse me. A conditional, you do one thing or another. It's either true or it's false. You have some condition. One arrow coming in, one arrow going out. Notice the process boxes, one arrow in, one arrow out. We can have an iteration, looping, in which we make a decision. If it's a leading decision, if it's true, we perform these instructions and we keep looping until the condition becomes false, and then we leave the loop. That's considered a do-while, do, and then we indent. Here are the instructions, and an undo. That's iteration, leading decision. Here, this is an iteration with a trailing decision. We do, we indent the processes, we have an undo. Okay, the decision's at the end, so we process. If it's false, we don't get out of the loop. We don't get out of the loop until it's true. Trailing decision. This is pseudocode. This is all lined up. If, and we have a conditional, we do this if it's true, else. This is indented. Else, we do these steps, and then an end if. Those are our control structures. Okay. So, I already talked about solving a problem. Okay. Do the analysis first. Make sure you understand the problem. Then you design a solution using flowcharts or pseudocode. At first, we'll use both. Then you develop the solution by writing the code and testing it. And it reaches a certain quality assurance. You make sure it's at a certain point, then you can implement the code. Have people actually use it and evaluate. Okay? So, to understand a problem, we do an IPO. Okay? Sometimes it starts with the output. This is what we want out. This is what we have available put in. And then can we use a computer to perform the process to actually move from here to here. Take the data and produce information. Alright, so let me finish up here. We have, for flowcharts, we have a box, a rectangle that we use for processing. Sometimes we'll use an equal sign, calculate what's over here, store it into this variable location. We can have diamond, which is a decision or conditional. Or often called a decision box. Okay, for an example, one arrow in, one out, one arrow in, two arrows out, depending on how you want to draw it. We have initialization, in which we can set things ahead of time. One arrow in, one arrow out. Start and stop for an oval. or they call it a terminal, with a 0 for a connector, and then we use a parallelogram for input or output. Alright, that's enough for today.